A and P students, we are back again for another lecture. That's what I always say, we are back again for another lecture. I need a new opening. I'll take suggestions from any of you if you got anything better. Anyway, we were just talking about pressure. Pressure is what is going to drive blood flow. Now we got to kind of switch gears a little bit and talk about resistance. Resistance is that which opposes flow. Primarily, it's a measure of friction. And the majority of this friction, and thus resistance, is encountered in your little arteries, your arterioles. And as such, because these are not major vessels, we talk about peripheral resistance when we talk about arterioles and their resistance. And the really important thing about resistance, about opposing blood flow, and you may think about it, why do you want to oppose blood flow? Well, here's the deal. You can't get all the blood to flow everywhere at the same time. This guy is running right here. He wants the blood flow to his quads, to his gastrocs, to his hammies, to all go up. Thus, he wants the resistance in these zones to decrease. But that means he's got to deny blood somewhere else, maybe to his colon, for example, to his gut. And so the resistance there would increase. So the big point of resistance, as far as its functional value for you, me, and this dude, is it's going to let you direct blood flow. We got to figure out how that occurs. Now, in doing so, we got to kind of take a step back and realize there's actually three sources of resistance: blood viscosity, total blood vessel length, and vessel radius, which, as you notice, I bolded it and underlined it there because it is the most important of the three. Okay, so viscosity. Viscosity, of course, is synonymous with thickness, and viscosity is directly proportional to resistance. If something is more viscous, it's got more resistance. Two examples of viscous fluids right here. I suggest you try and eat either one of these with a straw. Go get a Wendy's Frosty and try and drink it with a straw. Good luck. Try and drink a nice cold glass of ketchup with a straw. Good luck with that one too. It is not going to work because both these liquids are too thick. And by being too thick, they're going to experience too much internal friction and too much resistance. Okay, well, let's get anatomical and physiological here for a second. What is the major contributor to blood viscosity? Well, blood viscosity is primarily due to red blood cell count. All right, now, does your red blood cell count change very much? No, of course not. You're in homeostasis. It's not going to change. I mean, granted, if you have some disease process, if you are taking synthetic EPO, or if you are changing altitude, if you're moving to Peru, for example, it's not going to change. So it is, in you, it's not going to change. And even if it did change, well, heck, it's going to change everywhere at once. You need to be able to direct blood flow. Changing viscosity ain't going to let you do that. One quick question at the bottom here. What would an increase in plasma EPO levels do to resistance? Well, think about it. EPO is erythropoietin. Erythropoietin prompts erythropoiesis. So red blood cell count up, which means that blood viscosity is going to go up and resistance is going to go up as well. All right, good deal. Homework assignment for you. For next month, I want you to eat 1,000 donuts. 1,000 donuts in a month. And that's, what is that, like 33, 34 a day. If you do this experiment, you will get fat. You will gain adipose tissue. And if you gain adipose tissue, you'll grow new blood vessels. So your total blood vessel length will go up. And as total blood vessel length goes up, resistance is going to go up as well. A longer straw will have more friction than a shorter one. A longer straw will have more friction than a shorter one. That just makes sense. Now bear in mind, if your resistance goes up, it puts a greater workload on the heart. So the heart has to generate more pressure. Think about this. If someone goes to the doctor and's got high blood pressure, one of the first things the doctor is going to say, if that person is a little overweight, is going to say, you should probably lose some weight. Because if you lose some weight, you lose some vessels. You lose some vessels, vessel length goes down. Vessel length goes down, resistance goes down with it. Alrighty. radius. So this is an inverse relationship here. Notice that radius is in the or at the bottom right there. Okay, the denominator, if you want to get technical, and so resistance is proportional to 1 over radius. So radius gets bigger, resistance gets smaller. But check this out. It's not a direct one-to-one relationship. You got to take radius to the 4th power. So for example, if radius tripled, then resistance would drop by a factor of 3 to the 4th power, which of course is 81. 3 times 3 is 9, times 3 is 27, times another 3 is 81. So the point of this here is a small change in radius will create a big change in resistance. And this is one of the major reasons that radius is the most important factor impacting resistance. All right, so question for you. Does vessel radius change in normal healthy people? Yeah, absolutely, all the time. In your arterioles. And that change can be achieved by a variety of methods, including one we mentioned a while ago, which is norepinephrine release. If we adjust norepinephrine release, here we got more action potentials, more norepi, and we got vasoconstriction. Fewer action potentials, less norepi, vasodilation. So we're adjusting radius. We can totally do this. And we can do this regionally. We can do this locally. It doesn't have to be body-wide like the other two. And this alone is going to let us adjust resistance so as to achieve directional changes in blood flow. Awesome. 2 questions for you to do on your own. Easy ones. Just kind of summing it all up here. Resistance is directly proportional to length and viscosity and indirectly proportional to radius taken to the 4th power. All right, so another set of questions here. Which of these tubes would have the least? Which has the greatest resistance? Make sure you do these. Check your answers with me if need be. All right, so now what we can do is kind of sum up the things that affect blood flow. Blood flow is going to depend on 2 things. The larger the pressure gradient, well, the better the flow. The larger the resistance, worse flow. So for example, if you wanted to increase total blood flow, you would want to make that pressure gradient get bigger, so your cardiac output would need to go up. You can't see it, but I'm pointing my hand directly in the air as high as I can. I don't know why I'm doing that. I'm not like being video recorded here, which is good. Meanwhile, not only do you make your pressure gradient get bigger by increasing your cardiac output, you vasodilate in order to yield lower resistance. And that combo creates more blood flow. Similarly, if you want to drop blood flow, well, you want cardiac output to drop. That'll reduce your pressure gradient, which will mean less blood, will be less of a driving force on blood. Plus, you want to vasoconstrict, greater resistance, greater opposition to flow. All right, folks, we're going to quit right there. I will see you all later.